Okay, so this lecture is going to be entirely devoted to doing examples of rate of change. Some of these can get really tricky, so we're going to start small and then build up. I'm going to do it in such a way so that the first bit of the lecture we're going to be only doing average rate of change problems, and then the second bit we're going to be doing only instantaneous rate of change problems. Typically those ones tend to be harder. And then in the last bit we'll see some word problems. Okay, so that's pretty much how this lecture is going to go. Try and follow along, try and do the examples yourself once you think you've got a hang of how to do them. Of course, I probably don't expect you to be able to do the first few examples right off the bat on your own. So just pay attention, and hopefully the method for solving these is going to become apparent as I go through more and more of them. Okay. So the first one is an average rate of change problem. Okay. And this one is just going to be purely graphical. So I'm going to draw a graph, and then I'm going to ask some questions about rate of change. Okay. So I've put 5 problems on the board. I want you to try all of these. Use the definitions of velocity and speed that we discussed last lecture. Okay. So let's start by doing the first one. Now, actually, what I'll do is that I'll put some information that will help us throughout each problem. So firstly, remember velocity. Velocity is displacement over time, and speed is distance over time. So in the top 3 questions, we need to calculate displacement. In the bottom 3, we need to calculate distance. And time is pretty easy because, you know, we're given 0 to 5, 0 to 3, 0 and something else, right? So the time here is just going to be like 5 seconds, or this is going to be 3 seconds, and so on. Okay, so I'm going to gloss over this detail as I'm going through the examples. It's more the displacement that I'm worried about. So average velocity, what we're going to do is we are going to take the initial position and final position, right, at 0 and at 5. So we're going to take the final position, so f of 5 minus f of 0 divided by the time minus that, so 5 minus 0. And this is equal to 3 minus 0 is 3 over 5. And that's it. That's the answer to the first one, so the part A. For part B, we want the average velocity on 0 to 3. So what we're going to do is calculate displacement again. Your displacement as you went from here to here was exactly 2. You didn't change direction anywhere, right? No, this is a velocity, so you need displacement. You only care about the first part and the ending part. So all we need to do is again use our formula for displacement, f minus 3 minus f 0 divided by 3 minus 0, and this is quite simply 2 over 3. Okay? So hopefully that's not too difficult. The next part, I'm just going to machine gun fire through these. Again, in the exact same way, we get f of 2.5 minus f of 0, all of that over 2.5 minus 0. So hopefully you see this is the easier question to answer. This is equal to what? 2 over 2.5. If you don't like the fraction in the denominator, this is the same thing as 4 over 5. Okay. And you're allowed to use a calculator for these. Don't be afraid to use a calculator. I'm going to use a calculator to make sure that this is correct, although I'm pretty sure it should be right. Yeah. I was going to give up math if I got that wrong. Alright, let's do D and E. Those ones are the harder ones because you have to think about speed. Speed requires distance, and it takes into account how much you actually traveled. So on 0 to 5, what actually happened? You went from here to here and then stayed a bit for a while. So you covered, what, 2 meters, right? In this entire time you covered 2 meters, and then you covered 1 meter going back here, and then another 2 meters going back here. So your distance on the interval 0 to 5 is equal to 2 plus 1 plus 2. Okay, and this is 5, right? And because the time is 5, our speed is just distance over time, so it was 1 meters per second. Okay. For me, units are optional. I'm often going to give you problems without the units, so you can just put a number. Okay. However, when we get to the word problems, Often those will be done with a disguise of units on your problem. So you'll probably have to you'll most likely have to put units. Okay. Average speed on 0 to 3. Well, look what happened on the interval 0 to 3. You went 2 meters and then just stayed there. So the total distance that you traveled was actually just 2 meters. So this should be just 2 divided by 3. Then, that's your answer, right? So that's the answer for E. Okay. So that was the 5 problems for average velocity and average speed. Let's do 5 more using a different graph. One that will sort of dip into the negative region. So you may be wondering, what is meant by negative displacement? Well, maybe it's more clear if I give you a direction here, right? So if this is like north, and you're thinking about the negative direction, it makes sense to call this south. You're just going like the opposite way from north, right? So this is -1, -2, and so on, okay? So we're going to do a graph that does this. Do that, do that. Okay, and then we're gonna go back here. Okay, all right. So the questions I want to ask, whoa, that is a very crooked line. The questions I want to ask are, firstly, what is the average velocity on the interval 0 to 4? Then average velocity on 0 to 3. Then I want to ask what your average speed was on 0 to 4. And then I want to ask what your average speed was on 0 to, let's do 2. Okay? So try and work through those ones. Given the first example, these should be not too much different. Okay? Pause the video, work on them on your own. Alright, so for part A, all we are doing is taking the average velocity, right? So we just use the same formula we've been using this whole time, f of 4 minus f of 0, all that over 4 minus 0. Yeah, okay. So you do this, and you get 4. F of 4 is -2, and f of 0 is also -2, so you get -2 minus -2, minus -2. Be very careful about this one, and it's just 0. Okay? It's 0 over 4, which is 0. Now, keep in mind that this bottom here is not always going to be 0, right? You have to take the difference between the two times. Here I've been nice, I've given you 0 the whole time, but that doesn't mean I can't change it up a bit. This could have been a 1, for example, okay? So, let's do part B now. So part B is to find average velocity on the interval 0 to 3. So what you do, again, is you take f of 3 minus f of 0, all that over 3 minus 0. F of 3 is just 2, minus, and f of 0 is -2. Again, be very careful about this one. This gives you 4 over 3. So that's your average velocity. Okay. Next, for part C. For part C, we're going to calculate average speed on 0 to 4. What did you do on the interval 0 to 4? You went up 1 meter, 2 meters, 3 meters, 4 meters, and then you went down back to where you started. So you went 4 meters up and then 4 meters down. 4 plus 4 is 8, so you actually traveled 8 meters. Your distance on the interval 0 to 4 is equal to 8 meters. Okay? Therefore, your speed is 8 divided by 4, which is 2 meters per second. Similarly, part D, we can do the same way, except now we're just talking about 0 to 2. So from 0 to 2, you just went one way. You just went straight up, right? And you traveled 1, 2, 3 meters. So that gives you 3. So distance is equal to 3 meters. And your time is also equal to 2 seconds, sorry. And then all you need to do is divide the 2. So your speed is 3 over 2 meters per second. Okay? Hopefully that's not too hard. Right. So let me just, because I haven't done one yet, let me just show you what it would look like if I changed one of those time intervals. Let me pretend I want to change it from, let's calculate now the average speed on the interval 1 to 3. Okay? Let's see. So what you need to do is look at 1 and look at 3 and see how much distance you traveled from 1 to 3. And it looks like you just went straight up, so you just went 2 meters. Okay? So your distance is 2 meters. Now your time is not 3 seconds, but it's actually 3 minus 1, which is 2 seconds. So time is equal to 2 seconds. Therefore, your average speed is equal to 1. Okay? Just a quick example to show you what happens if that number is not the one that you want. You will always have a smaller number, bigger number. I'm not going to give you like some crazy interval that's like 3, 1. That doesn't make sense. Okay? Yeah, we've gone to the point in the video where I think that's all I wanted to do with average speed, because these ones are the easier questions. Now we're going to go through how to do the instantaneous rate of change questions, okay? All right. So, instantaneous rate of change. The first example, I don't expect you to be able to do on your own. So we're going to go through this one together and then use this example to maybe motivate how you would do the rest of the other examples. Okay. So we're going to do instantaneous rate of change for x squared. Okay. X squared at x equals 2. Okay. So remember, we had two ways of doing this. We had this method, the x minus a method. And we also had the h method. Right? These were our two methods for evaluating this difference quotient. So I'm going to show you actually how to do it both ways. Okay? That way you can decide which method you like better. Personally, I think for this question, this one's the better method. Okay? But this is, again, all up for you to decide. The fact that there's two methods is not here to confuse you. It will actually help you in the long run. Sometimes one method is better than the other. We're going to see that today a little. Okay? So how are we going to do this? Well, remember what this actually means. This actually means that x gets closer and closer to a. And what is a in our problem? A is just x equals 2. It's all the a's with just a 2. Okay? So if you understood the formula and what it actually was doing, this should not be too difficult. Just graphically what's going on, I'll put it up here maybe, is that we have our function x squared, and at 2, we want to figure out what the instantaneous rate of change is, which means if I draw a tangent line to x squared at the point 2, 4, I want to know what the slope of this line is. Remember? So what this is doing is I'm going to pick points that are close to 2, right? Close to 2, figure out their coordinates, and then draw lines from this point to that point. That gives me a line. But then what I want to do is I want to move this point closer and closer to 2, and that's how I'm going to get a good approximation for this limit. Okay? So that means I need to choose points that are close to 2. Let's choose points that are close to 2. Think of some points that are close to 2. What I wrote here was 1.9, 1.99, 1.999. The reason why I have 3 is because I want to see if there's like some pattern. Maybe like 1.9 is too far, you know? Maybe 1.99 is a bit better. Maybe, 1.999 will be definitely a lot better. So I'm just going to try 3 just to make sure, like it's consistent. And then I'm going to also do the other side. The reason why I'm doing the other side is because, remember, in order for a limit to exist, both sides have to agree. This equates to, I don't need to just pick points from the right, I also need to see if they work from the left. So I actually need to make sure that this limit even exists. Now, just really, really putting it out there, this limit is not the same thing as evaluating the function. Okay? This is an entirely new thing. We don't know what this looks like. However, what it does tell us is the slope of tangent lines. Okay, so as I pick points that are around 2, all this does is that it draws a line and tells you the slope of that line. Okay, it draws you a line between the 2 points and tells you the slope of those lines. So what that means is that we need to set x to equal to all these values, plug it in here, see what happens. Set x to all these values, plug it in here, see what happens. Okay, and that is how we are going to get around this limit part, because this limit part is the thing that's difficult to understand. Okay, so to do this, we're going to make a table. We're going to evaluate the expression f of x minus f of 2, x over x minus 2, at all of these values of x. So get out your calculator, start plugging them in, you'll get the following values. So remember, f of x is x squared, so maybe it would be better to just write that down, right? So what we're going to plug in x for is x squared minus f of 2 is just 4, all that over x minus 2. Okay? So we're going to plug in all these values here, see what happens. Okay? Now, I want you to go ahead and do it, but before you do that, realize that there's something really, really clever that you can do. And it's just factoring, right? You look at this and you say, haha, I can factor it. And you can factor it because this top part is a difference of squares, and this bottom part is just x minus 2. So you kill these two, and you're just left with x plus 2. So I don't have to use this messy thing, I can just use this thing. Okay, so let's go ahead and do that. Plug in numbers. So maybe you could just do it by looking at it. Okay, the first one here, so we'll call this big expression exp for expression. Okay, we are trying to evaluate the expression. Okay, so, and the expression we found out is the same thing as x plus 2. So let's just do that. This is going to give you 3.9, 3.99, 3.999. You can use a calculator, or you can just add in your head. Then when I do this one, what's it going to give me? It's going to give me 4.1, 4.01, 4.001. Okay? As these numbers here get closer and closer to 2, what does it look like these numbers are getting closer and closer to? You just have to look at it and you'd say, they're getting closer and closer to 4. So our guess is that this limit thing, this whole thing here, is equal to 4. The limit is equal to 4. So 4 is our answer, right? And what that means, graphically, is that if I drew a tangent line here, that means I would expect its slope at this point, x equals 2, to be equal to 4. Okay? So our slope, or instantaneous rate of change, at x equals 2 is 4. Okay? Now we are going to do it the exact same way. Now, what was this h method again? Well, that was just taking into account that these points here, I don't have to consider them as numbers like I did here. All I have to do is consider them as some distance away from 2. So that means I just have to pick small values of h, right? And see what happens as those values get closer and closer to 0. That's how I'm evaluating these, right? So just to rewrite this in a way that would make more sense, so this is the limit as h approaches 0 of, remember f is just x squared, so we can do x plus h squared minus, well, f of x is x squared, so we'll just do that, right? And remember, the really annoying thing about the x, the h method is that x is actually this point here. So we have to replace x with a 2, and then we're ready to go, right? So to evaluate this expression, before we do that, actually, let's just see if we could simplify some things here. So look at the top, right? This becomes 2 squared plus 2 times h plus h squared, because of adding two things and then squaring it. This is what you get, minus 2 squared, okay? 2 squared and minus 2 squared cancel out. 2 times 2 is 4. 4h plus h squared over h is just equal to, well, you can factor out an h, right? So you get 4 plus h times h all over h. And these h's cancel out, and this gives you 4 plus h. So this is why the factoring is really important. If you did not see this, you would have to go and plug in the values of h into this expression, and this is really messy, right? Whereas this one is really nice. 4 plus h is really easy to work with. Okay? So what values of h do I need to use? What values of h do I need to use? I need to use values of h that are closer to 0. So let's take some values that are close to 0. I can think of 0.1, 0.0001, and 0.001. But there's also the negative side. Remember, we can't just approach from one side of 0, we need to approach from the other side of 0. So we need to go negative 0.1, negative 0.01, negative 0.001. Okay? And then we are going to evaluate this expression, right, at all of these values. But we just saw by factoring that this expression is the same thing as this one. So really we're just going to be using this. Now if you plug in all these numbers for h into here, what you get is 4.1, 4.01, 4.001. This is, let's see, 3.9, 3.99, 3.999. You can check with a calculator, or if your mental math is good, you should be able to see these pretty easily. But the point is, as each of these numbers gets closer to 0, these numbers get closer to 4. You just have to look at them, like, 4.1, 4.01, 4.001, it's like they're getting closer and closer to 4. This one is getting closer and closer to 4 as well. So it looks like the answer here is, again, 4. So slope, or instantaneous rate of change, at x equals 2 is 4. So we have the same answer as we did there, which is good, because if they were different answers, that would mean that one of these is wrong, because obviously, like, there's only one line that's going to work. You can't have two different answers. It has to be the same answer. So this is good. So I've shown you how both methods work. In the examples that follow, I'm not going to show you how both methods work. I'm just kind of like alternate between them to give you a little bit more exposure to each. Okay? So let's choose another example. Let's choose an example. It's a little bit more complicated than x squared. I'm going to choose the function. We're going to pick cosine x, f of x, and we're going to do 2 cosine x minus 1. Okay? Alright. So here's the problem now. Before, we had a graph to sort of, inform our intuition. This one you can graph it, but I'm not going to. You can graph it if you want, but I'm not going to. You should get into the habit of not having to graph things, because the algebra that we go through should be enough to inform you what is right. So next, let's see, I'm going to evaluate this as x is equal to, I think I'm going to do 0. Yeah, let's do 0. Okay, so at x equals 0. And I'm going to use the x minus a method. When you're doing your homework, you don't have to tell me what method you're using. I'll know just by looking at it. But if it's, it should be clear what method you're using, right? Don't change the letters or anything. Okay. So remember the x minus a method, we have to use this expression. Limit as x approaches a, f of x minus f of a, all that over x minus a. Okay. I know it looks like I'm writing it way too fast for someone who has done this who has not done this in a very long time, but I promise you that as you get good with it, you're not only going to be able to memorize this formula, you're actually going to understand why it works if you didn't understand it the first time I presented it. Most people don't understand it the first time, but if you really, really think about it, you will see that this is literally saying this is the slope of the tangent line. Okay? But it might take a while to develop that sense of what these things are saying. The really nice thing that I find about math is that we can translate these ideas that make sense in our head, but are hard to put into words, and we can just write them down using this notation. Okay. All right. Let's see. So we wanted x equals 0, right? So that means everywhere we see an a, we have to replace with 0. So let's do that right now. 0, 0, 0. And see what happens when we simplify things out. Well, okay, first really easy thing, x minus 0 is just x. Good. The next thing that I see is f of 0. What is f of 0? Okay, well you have to put a 0 into here. So we want 2 times cosine of 0 minus 1. You can use your calculator. You'll find out that this is equal to 1. So we can just replace this f of 0 with 1. Okay? F of x is equal to 2 times cosine x minus 1. So that means we have limit as x approaches 0 of 2 cosine of x minus 1, all that over x. Okay? Doesn't work out as nicely as it did last time, but that's okay. We're going to go through it anyways. Okay? Now, the next thing you can do is minus 1 is minus 2. Okay? And that's about all that I can see would be helpful. You can factor out the 2. It's not going to do much. You're going to have to multiply by 2 anyways. Okay? So let's try and evaluate this bad boy. Alright. So what does this limit here tell us to do? We need to pick values of x that are close to 0. So what are some numbers close to 0? You'll see that my pattern is pretty much the same every single time. I just pick 0.1, 0.01, 0.001. Negative 0.1. Remember, I have to do the other side as well. Negative 0.1, negative 0.01, negative 0.001. Okay? And these numbers are getting closer and closer to 0. Okay? Then, here's my expression, right? So I need to evaluate this at all these values of x. Grab your calculator and let's do it together. So 2 times cosine of negative 0.1 minus 2, and then divide it by 0.1. And that's like a really small number. It's like I'm getting negative 3.04 times 10 to the negative 5. Very small. Okay. What happens if we replace that whole thing with a 0.01? So again, I'm going to type in 2 times cosine of 0.01 minus 2 all over 0.01. If I try that again, I get an even smaller number. It's like 3.04 times 10 to the negative 6. And then if I type in an even smaller one, 0.001, this is getting a little predictable. It's 10 to the negative 7. So it looks already like these things are going to 0, right? This like, power here is getting closer and closer. It's getting larger and larger, so it looks like these numbers are getting smaller and smaller. Meanwhile, if I try it for negative 1, let's see what happens. So negative 0.1, top 1, negative 0.1. All right, it looks like I've got the exact same value here. And I'm willing to bet that if I put 0.01, yep, it's the exact same value here. And if I put 0.001, well, it's the exact same value again. So it looks like these are all going to 0. So that means this expression, as x approaches 0, this whole thing is going to 0, which means our instantaneous rate of change at the point x equals 0 is 0. Now what does that mean, to have a 0 instantaneous rate of change? To answer this question, I'm just going to quickly graph it. Now, I'm not going to go through in detail the steps of how I graph it, but you can use Desmos if you're uncomfortable with graphing these. I'm just going to tell you it's going to look like this. So this is 1, this is negative 1, this is negative 3, and this is cosine, so it should look like this. Okay? So this is what your graph should look like. And remember, we were considering the point x equals 0, right? Now, why did we do this whole thing in the first place? Right, we were calculating instantaneous rate of change. And instantaneous rate of change means we're calculating a tangent slope. So where's the tangent slope here? Well, if you look at it, the only line that is like going to kiss it at x equals 0 and then leave it is a flat line. Okay? Because you can just see it it's like a roller coaster. As you approach here, it's like getting flatter and flatter. Okay? So this makes sense because the slope of this line is 0, and we just found out that our instantaneous rate of change at x equals 0 is 0. Okay? So our graphical method lines up with this. But you can't just draw the graph and say, aha, look, it's 0. You have to actually show it using the methods that I've just shown you. Okay? One more. Let's do one more. We are going to do the function 3 to the x. But not just any 3 to the x. We're going to do 3 to the x plus 2. Okay? At x equals, let's do a nice number, 3. Okay? And figure out what that is. Okay? This one I can tell you might get a little messy. Okay? Okay. First up, actually, I don't think I want to do this one. I think I want to. Okay. It's about time you learn about this this function e. So on your calculator, you'll notice that right above your lawn button probably is a button that says e to the something. What is e? Don't worry what e is. E is like a number. E is a number, and if you just try it, if you just try seeing what e is on your calculator, it's like 2.71 something. Okay? It's just a number. Why are we so interested in 2.71 blah 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 blah? It turns out it has some magical properties, and we are going to see that when we do this question with e, the answer is going to be, you know, a lot nicer. Okay? It might not be what you expect. Okay? Yeah, okay. That's all I want to say about that. I could go a little further about e, but this is not the point of what we're doing today. So now let's do it using the x plus h, using the h method. We're going to do this using the h method. Again, this is really up to you to decide on how you want to do this. Sometimes they're going to be useful one way, sometimes they're going to be useful another way. Okay? But in this case, actually, the h method is harder. So I would encourage you to try it using the x minus a method, and then try doing it with the h method. Make sure that the two answers line up, and if they don't, look at what I'm doing here. Okay? All right, so remember what's the h method? It's the limit as h approaches 0 of f of x plus h minus f of x, all of that over h. What is f of x? Well, remember here, x is equal to 3. So we'll replace a x with 3 everywhere. Okay. Now we're going to evaluate it using the function. What is e to the 3 plus 2? It's just e to the 5. Don't try and come up with a nice number for it. It's not nice. It's just e to the 5. Okay, e to the 5. What is f of 3 plus h? Well, I just replace x with 3 plus h. So that means e to the 3 plus h plus 2. But this is the same thing as e to the 5 plus h. Okay, so I'm going to replace this thing with e to the 5 plus h. E to the 5 plus h. Right? Okay, so this is our expression. There's not really a nice way to simplify it. You can. It's not going to make your life a whole lot easier, to be honest. So let's just stick with this for now. This will get you some good practice using your E button. Okay. So to evaluate this limit, again, because this is h approaching 0, we need to pick values of h that are close to 0. It's the same thing every time. 0.1, 0.01, 0.001. And then you take the negative side, 0.01, 0.001. And then we're going to just plug it all in, see what happens. All right, so get to work on your calculator. I'm going to do it on mine. I might cut the video here just to tell you, just like with all the numbers there, just to show you what it is. Okay. Okay, so here are the numbers I got. These look not nice. They're not, you know, the nice numbers that we were getting before. I can't even tell what this is approaching. It's like 148.4 something, right? It's 148.4 something, and this one, it looks like it might be going to the same thing. So, you know, like some number between 148.4 and 148.3 maybe, but besides that, that's all you can tell. And this is the point that I want to make. sometimes this method doesn't work. This is a very bad method for evaluating limits. This is just what we happen to get on this occasion. Now, I want you to try something, and that is finding what e to the 5 is. What is e to the 5? It is 148.41 something something something. Okay? And it turns out, I'm not going to tell you why right now, but it turns out that these two numbers are actually getting closer and closer to this, e to the 5. Okay? It's not obvious at all. I don't expect you to be able to do this, but this is like I'm just trying to show off here what calculus can do, because I knew that the answer was e to the 5 from the very beginning, just because I could do some calculus in my head. It wasn't too difficult, and I got that number. So here's a really bad way of doing it, but using calculus, you can get the number in your head. Okay? So, I think that's the last regular example that I want to do with instantaneous rate of change. I think maybe let's do 1 or 2 word problems and then see where that leads us for time. I think we're going to be pretty much, I think we're going to be pretty strapped on time by the end of 2 problems. Okay? But yeah, don't worry too much about this example. The only thing that I want you to really get out of it is the method for plugging in values of h on both sides, right? So remember, both of these going to 0, one from the positive side. Sorry, I forgot to put negative signs here. And one from the negative side. Hopefully that didn't mess you up too much. So now I'd like to begin working on some word problems. We're going to do 2 word problems. Each of them is going to have multiple parts. And the way this is going to work is that the first problem is going to be a direct application to a non-math field. And the second one is going to be an application to more math. So in the second example, we're going to see a literal calculation that is going to be done in calc and vectors. So let's go ahead and get the first question out. So basically the situation is this. You're standing on top of a tower, okay? And the tower is 450 meters tall. Now what you do is you stand on the top of the tower, you drop a ball, and you want to know a couple of things about the ball. The first thing that you want to know is what is the velocity at 5 seconds. Okay? And the second question is, how fast is the ball traveling when it hits the ground? And lastly, we want to know what the average velocity and average speed were. Okay? This is a problem adapted from a university textbook. That might sound a little daunting, but don't worry, a lot of the university curriculum is direct overlap with grade 12. Alright, so here's the first problem. What is the velocity at 5 seconds? Oh yeah, right, sorry, I forgot to tell you. In physics, you learn an equation, and if you apply this equation to this scenario, you'll figure out that there's actually a function. This would be given to you on any homework or test scenario. They don't assume that you take physics. Basically, they assume that your position is negative 4.9 t squared. Okay, so that's your function with time. So basically, what would happen is that at time t, what you would do is you would, let's say after 1 second, you would put like a 1 in here, and then that would mean that you traveled negative 4.9 meters down, for example. Okay. All right, so what is the velocity at 5 seconds, okay? I want to sort of understand really what this is saying. When it says what the velocity is at 5 seconds, what they're really asking for is instantaneous velocity, right? Now, why didn't I put instantaneous velocity in the question? Well, that's because it wasn't in the question. So I'm doing this to illustrate that sometimes you got to read in between the lines to be able to understand what this is really asking, okay? So instantaneous velocity at 5 seconds, we can replace this here with t equals 5. Okay. Then this question is really asking, what is the instantaneous rate of change at t equals 5 for this function f of t? Okay, that's all there is to it. Okay. In fact, we don't even need the 450 here. All we need to do is observe this graph. So now we have a choice of options. We could use our methods. We could use the x minus a method, or we could use the h method. I'll do it the x minus a method this time. It just happens to be a bit easier today. So limit as x approaches a of f of x minus f of a, but in this situation a is equal to 5, right? Because we're looking at t equals to 5. So I should probably put a t instead of an x. Yeah, that would make more sense with the variables. So our a is 5, so we'll put 5, 5, and 5, okay? Now you can go ahead and plug in this number. What is f of 5? It's just negative 4.9 times 25 squared, which is equal to, 5 squared, which is 25. And that is equal to negative 122. So this is equal to negative 122.5. All right, so I can replace this with limit as t is approaching 5, f of t, I'll just replace it right now, negative 4.9 t squared minus 122.5, minus becomes a plus, all of that over t minus 5. Okay, all good? So what we're going to do is try and evaluate this limit. Of course, we have to use our really annoying method. So let's calculate this limit. First, I'm going to notice that there's not really much factoring I can do here. It's not really lending itself to some nice factoring. So I'm going to abandon that idea almost straight off the bat. So what's going to happen now is I'm going to try see if I can pick out numbers close to 5. So we'll go from the right side, so that'll be like 5.1, 5.01, 5.001, and from the left we get 4.9, 4.99, 4.999. Okay, and to sort of just cut to the chase here, I'm not going to evaluate these two. You should evaluate them just to make sure that you agree and like there's no problems here. So I'm just going to evaluate them at 5.001 and 4.999. Actually, I'm not even going to do that. I'm just going to tell you what the answer is right now using a bit of calculus. So you should be getting that these numbers here, as you get closer and closer to 5, are getting closer and closer to 49. So, sorry, negative 49. Let me just triple check here. Negative 4.9 times 5.01 squared plus 1225. All that over 5.001 minus 5. Yeah, I'm getting close to negative 49. Okay? All right. So that takes care of the first question. So this means that the ball is traveling down. That's what the negative sign means. It's traveling down at 49 meters per second approximately. Okay? And on a test situation, I would expect you to not put like the decimals. I would expect you to say like it's 49. It's negative 49. If both of them seem like they're getting really close to negative 49, it's a pretty safe bet to assume that it's 49. I typically won't ask some ridiculous questions that will give you ridiculous numbers. Okay. Now, B, how fast is the ball traveling when it hits the ground? Okay, well there's a couple of things here. How fast is the ball traveling means what is the instantaneous rate of change. So I'm going to cross all that out and replace it with instantaneous rate of change. Okay, that is a term that I understand. It's something that we've used in the unit. And this is where you can kind of cheat with math because you know what unit you're doing, right? You know that somehow this question has to involve instantaneous or average rate of change, right? So like don't try and interpret the question literally, try and see how to connect it to things that you already know in the curriculum, okay? The only thing that's a problem is when it hits the ground. Well, when does it hit the ground? That's a problem. Like I don't know when it hits the ground. So how are we going to do this? Well, let's write down what we wish we had. What we want is a t value for when the ball hits the ground. And we don't have that. But what we do have is all the tools necessary to solve for that. Okay? And let me show you how we're going to do that. So remember what we need is t, and something that I know about time and distance and all that is some relationship between how speed, distance, and time are all related to each other. So let me write that down. Speed is equal to distance over time. Okay. Now this this thing here, right? This 450 meters. The ball has to travel down 450 meters. So what we're really asking is, what value of t will have to go in here so that the distance traveled by the ball is negative 450. Okay. And if that doesn't make sense, you just have to think really hard about what this function is actually doing. Right? This is actually saying the ball is going down because it's a inverted parabola. Okay, so all you have to do is think about this, right? So the distance that you would travel in t, you want it to be 450, right? So you want your ball to travel negative 450 meters, right? And we know that the relationship with time is this. Okay, so notice how I wrote this thing down here and I never ended up using it. That's fine. That's fine. It's almost always a good idea when you don't know how to approach a question to just write down everything you know about all the variables involved. Okay? If it's a question about speed, distance, time, let's just put down the relationship about speed, distance, time. Eventually, the hope is that you become so good at solving these questions, you don't even have to waste time doing that stuff. But if you're still struggling, that's always a good first step. Okay? So that means we just have to solve this equation. I'm going to solve it real quickly. The negative signs cancel out. 450 divided by 4.9 is some number. I'm not going to write it down. 450 divided by 4.9. All I know is that this is equal to t squared. I want my t, the time, to be a positive number. Time can never be negative. Okay? Keep that in mind. I'll put it in a box right here. Time is not negative. Okay? So all you have to do then is take the positive square root, not the negative square root. Okay? So that means t is equal to square root of 450 over 4.9. Put that into a calculator, and I'm getting something like 9.58. Okay? So why do we do all this again? Oh yeah, that's right. We wanted to know when the ball hits the ground. So why does this help us at all? Well, now we can basically apply the same formula that we did up here, right? All we have to do is ask how, so now we know when it hits the ground. That's just t is equal to 9.58 seconds. And then we can just apply the same thing that we did in part A. Now I'm not going to waste time doing it another method or doing the whole thing again because I did it in part A. So what I'm going to do is going to ask you to do it. If you're uncomfortable with the first part, try and do this one yourself. And the answer that you should be getting is, you should be getting something like negative 93.88 seconds, meters per second. Okay. Now I know that the number there might not have been so nice, but like that happens to be the answer. Let me just triple check that. Yeah, I'm pretty sure that's the answer. Yeah, so it's around 94 meters per second. I wouldn't penalize you if you said around 94 meters per second. That's also correct. Okay. So now the only thing that's left is part C. What is the average velocity and average speed? This is a little bit of a trick question. The reason being because you know that the ball only traveled one way, right? The ball didn't go back up anywhere through here. So all you know is that the average velocity, the displacement is the exact same as the distance traveled, right? So displacement, remember, is final position minus initial position. So your ball traveled 450 meters, and distance is how much, literal distance you traveled, right? So in this case, it's literally the same. Displacement is the same as distance. So these two are the same. We don't actually have to do two calculations, it's just one. Right? With velocity, though, you might want to put a direction on it. That's the only caveat to that. All right. So remember, average speed, or average displacement, is equal to final position minus initial position divided by the difference in time. Okay. Now the difference in time. Well, t0 is just 0, right? So let's put a 0 here. Let's put a 0 there. Okay, sorry, this should be average velocity. Then t1, that's the time when it hits the ground, right? But didn't we just solve that here? That's right. So T1 is actually 9.58. All right. So if you plug all these in, you'll be able to get your answer. F of 0, I noticed right away, is just 0, so we don't actually have to care about any of this. And so our calculation just reduces to negative 4.9 times 9.58 squared, all of that over 9.58. Okay? And you should be able to do this pretty quickly using a calculator. It's just negative 4.9 times 9.58, and I'm getting negative 46 let's round it to 47. I'm getting around that. Okay? Negative 47 meters per second. Okay? All right, so that takes care of the first question. Right, and so this is velocity, right? For speed is always positive. Speed, remember, doesn't have a direction. The reason why we have a negative sign here is because the velocity takes into account that you're going down. Speed is always going to be positive. So really, you do get two answers, but the number is the same. So average velocity is that, and average speed is just the same number, but positive. Okay? If the ball were somehow going up, and this was the same function, but with a positive sign, then both of these would be the exact same. All right. All right, we are on the last question for today. I know it's been quite a long video with a lot of stuff to digest, but everything should now be beginning to come together. This is sort of the last, really difficult thing that you could ask about these concepts. But as we go through it, you'll see that it's really not that difficult. The actual doing of the question is not that difficult. It's just being able to understand and sort through the ideas that may be a little tricky at first. Okay? So what we have here is a question that is asking you to find a general formula for the instantaneous rate of change, right? And what this means is that for any value a that you give me, I should be able to tell you what the instantaneous rate of change of the function at that value is. So here we have root x, all right, and it looks something like this. And what this question is basically saying is, I give you a point. Let's say I give you this point, and I want you to be immediately able to tell me what the instantaneous rate of change at that point is. Now you might be thinking that's really difficult, because then we would have to do the whole thing that we did for the previous questions all over again, but for every single point possible. And yeah, it is really difficult, but that's what the beauty of a general formula is. Once we find it, we can basically get any point on here, and I can tell you what the instantaneous rate of change is. Right? So let's see how we would approach this problem. Okay. All right. And the second part we'll tackle later, but it's basically saying to use this formula and plug in these 2 points. Okay. All right. So again, what we need is the instantaneous rate of change at this point. Okay. It might look a little weird because this is not a number. A is not a number. It's a letter. It's a variable. But we're going to try it anyways. So really, right off the bat, you don't see any tricks here or anything. The only thing that's a little daunting is this part, right? If this a here was a number like 1 or 4, then it wouldn't be a very difficult question. We would just have to do the exact same procedure that we did in the previous questions. So what I'm going to do is I'm actually going to pretend like a is a number and see where that leads me. So the first thing I'm going to do is this. I'm going to try the x minus a method. Okay? I'm going to try the x minus a method and see what happens. Now there's no reason in particular that I'm doing this other than the fact that I might get stuck here. And I'm actually going to, I'm going to pretend I get stuck here because I want to simulate being in your position, seeing these types of questions for the first time. All right? So again, we pull out our good old formula. Instead of f of x and f of a, we're going to have root x and root a. So let's do that right now. Okay? All right, so now what can we do? Well, this is really frustrating because we still don't know what a is. All of this work that we've done hasn't really revealed much. And now how are we supposed to evaluate this limit? Well, I don't know, maybe we should try the exact same thing that we did the past couple of times. So, you know, remember how we were trying to get numbers close to A? Let's try and do that again. So we'll do like, I don't know, well, like it's a huge problem. It's like, what is A? If I don't know what A is, then how can I choose numbers? So, okay, maybe this way won't work. Maybe it won't work at all. Okay, so let's leave that there. I'm going to show you how to get through this in just a sec, but first I want to try the other method. See, if one way doesn't work, the great thing is that because of the way that the curriculum is designed, the way I've taught you, you actually have two methods that you can go on. And in this case, it happens to be that the H method works better because, look at this. Now, when you do the limit, you have a number, and you know numbers that are close to 0, right? We did this a bunch of times. So again, it's f of x plus h minus f of x, all of that over h. Okay? So let's see what happens. Again, the f's are just square roots, so we can replace this with limit as h approaches 0 of x plus h with a square root minus square root of x, all of that with an h. Okay, and remember the point that we are trying to evaluate is not at x, we're trying to evaluate at a, so I'll erase all the x's and put in a's. It's just a little detail that you should keep just to make sure that you don't lose track of what you're actually trying to do. Alright, so now we are trying to find the instantaneous rate of change, which means we have to evaluate this limit. How do we evaluate this limit? We just have to pick sample points near 0. So let's pick 0.1, 0, you know, the typical ones. Okay, we've done this so many times today, this shouldn't even be that hard anymore. Okay? Now, let's evaluate this expression at each of those numbers. Except, like, what are we actually doing? Because, you know, we don't know what A is, right? So if I were to substitute it in here, it would be like, let's put in a 0.1 for example. We would be putting like a plus 0.1 minus root a, all that over 0.1. Okay, like that's not going to work out. This doesn't actually tell you anything, does it? Okay, so it looks like we're stuck. Except for one little trick. And this is the same trick that will get us through this part. We'll use it here now, okay? And it's actually something that we've done in the course already, and that's rationalizing the denominator. You might be asking, but there's no rational in the denominator, like it's fine, there's no root sign. Well, we can use the same concept in order to try and get something to be a little different in these questions. So in my case, I don't like the fact that there are square roots here, right? I want to get rid of those square roots. So I'm going to multiply by something clever, and you should be able to remember that the something clever would have to be taking advantage of the difference of squares. This is the clever thing that I multiply by, right? In this case, you know, the difference of squares formula goes a squared minus b squared, equals a plus b times a minus b, right? So here, a is this thing, and b is this thing. Okay, I know it's confusing because A and B, but whatever. Okay, so just to be super clear then, what we're doing now is we're factoring this in a clever way and hoping something nice happens. And something indeed really nice does happen, and it's the following. Look. Okay, maybe you see it already if you're working through this on your own. If I multiply these two together, I use the difference of squares formula. This just gives me a plus h. Right, because the square of this value is a plus h, and the square of this value is a. So it's a plus h minus a, all of that over h times the messy thing in the denominator, root a plus h minus root a. Aha, but the a and the minus a cancel out, and then the h's cancel out. Okay, well that's good. But did this actually solve our problem? I'm going to convince you that yes, it did solve our problem. Okay, so look at this. Now let's try and think about the limit. So we have x is equal to 0.1, 0.01, 0.001. And my approach to this one is not going to be so much plugging in these numbers, but actually thinking what is happening as these numbers get closer and closer to 0. Okay? So let's think about it. So first I put in a 0.1, right? Okay, not much happens. And I put in 0.01. Again, like I can't really evaluate that because I don't know what A is. But as these numbers get closer and closer to 0, this little h thing, it matters less and less, right? I'm going from, okay, maybe I shouldn't do it here. Actually, yeah, I'll do it here, So we're going from a plus 0.1 minus, sorry, these should be pluses, I just realized, my bad. Plus root a, right? And then we're going, when we put in the smaller number, it's like a plus 0.01 plus root a. And like it's just getting smaller and smaller. And eventually this number is going to get so small it doesn't even matter anymore. So really, this looks like it's getting closer to, I would guess, it's getting closer to root a plus root a. Oh, but that is just 1 over 2 root a. Okay? And I want you to think about this one and see that you actually should be approaching the same thing. Just in your head, it should make sense that as this number gets super small, it becomes like nothing, it becomes negligible, so negligible that you can ignore it completely, and then you can just do this. Okay? Now, I want to be very cautious here and say I'm not directly putting a 0 into here. I can't do that. I have to actually think about the limit. I can't just plug in a 0. Okay? Alright. So, with that being said, so this is the answer, right? 1 over 2 square root of a is the answer. But let's see if we get the same answer. Inspired by this idea, we're going to try the same thing here and see if we get the same answer. And we better get the same answer or else math is broken. So 1 over 2 square root a is our answer. I'll just put it in a box right there so that we remember. Now, let's try the same thing here. Again, the idea is I want to get rid of square roots. Square roots are nasty. So I'm going to multiply by this. And this will hopefully cancel out somewhere. I don't know what exactly it will cancel out yet, just by looking at it, but I know maybe it will work because, you know, it worked there. Why wouldn't it work here? Maybe you hope that it's true. Right, so I'm just going to do the same algebraic work. I expect you to be able to follow along. And if you cannot, take a minute, try and make sure that you understand completely how I got to this. Alright, so first thing I see is that I can factor out some stuff. That would be the x minus a here and the x minus a here. All good? Then, all we have to do is limit as x approaches a of 1 over root x plus root a. Okay? Now, what is going on here? I need to pick values of x that are very, very close to a. Think about it in the exact same way how we thought about this one, and you should realize that as x gets closer and closer to a, this value, 1 over root x plus root a, is actually getting closer and closer to 1 over root a plus root a. That's just because root x is getting closer to root a. Okay? And then this is once again 1 over 2 root a. And math is not broken, we're happy. Alright, so our answer is 1 over 2 root a. You give me, let me just remind you why we did all this work and what the question was asking. Remember, we were trying to figure out what the instantaneous rate of change at any point was. So now we have that our formula is, so for x equals a, the instantaneous rate of change at the point x equals a, I guess that's kind of redundant. The instantaneous rate of change is given by 1 over 2 root a. Alright. Now you may be thinking, this is an expression, and it gives me the power to basically put in any value of a that I can think of in here. Okay? Doesn't that sound a lot like a function? So keep that in your head, and we are going to see that this interpretation is exactly what we are studying in calculus. Like, right now, this is no joke, this is literally what calculus is, right? Okay? But we're going to stick to this question for now, right? So to finish it off, we'll plug in x equals 1 and x equals 4. We do this, we get 1 over 2 for the first one. And if we plug in a 4, we'll get 1 over 4. Okay? So hopefully you find that a little interesting, how we can just use the definitions of a slope of a line and the idea of a limit to get these ideas of instantaneous rate of change. Okay? And now we've done something so powerful with this. I don't know if you realize, but this is really, really powerful, because this is saying at any point on the graph, I can tell you how fast the graph is evolving, how fast it's increasing, how fast it's decreasing. Okay? And those are ideas that I want you to keep in mind as we go through this course, because this question of instantaneous rate of change is not restricted to this unit. I can ask you questions about instantaneous and average rate of change throughout the entire course, because this is such a fundamental idea that is going to carry over to calculus. Okay? So that's all I wanted to do for today. This concludes Unit 2. It only took 2 lectures, but starting next lecture, we're going to be moving on to the bulk of the course, which is literally studying functions. So this whole first 2 units has just been ideas about functions that we can study, and now we're going to apply these ideas to all the different types of functions that are most commonly used in the real world. Okay?